So let's get started. Good morning, everyone. My name is Chao, and I'm from Intel. Today, I'm going to talk about how to achieve the QoS in server virtualization by using Intel platform shared resource monitoring and control technologies in the latest thing. But before talking about how, I'd like to talk about why. So why we need the QoS? The virtualization has been widely used in the industry for more than a decade. So why we need to care for the QoS at this time? Although the virtualization technology itself seems stable, it is still on its way of environment. Recent years, the environment of virtualization has led to several typical usage models. One usage model is putting traditional enterprise IT services to private or public clouds. Nowadays, it's quite common for a public cloud vendor to provide different classes of services to different customers. Then they need a way to make sure the quality of services for each classes of customers are satisfied, just as they had written down in the contract. I think the same QoS requirement also applied to the private cloud, as the only difference for private cloud is its customer are internal. Another typical usage model is network function virtualization, which migrates the traditional telecommunication services to general virtualized platform to leverage the benefits of the virtualization. So there's intrinsic QoS demand for the telecommunication services. So in the past, it's achieved by using some optimized dedicated system. Now, after they migrated to the virtualized environment, so the same, or at least the same QoS requirement should be guaranteed. Okay. So the QoS requirement for virtualization has been changed from the better to have in the past to nowadays must to have. Okay. Then the next question is, what's the current status? Are we already ready for this, or there's still something we need to do? Let's say our thread contention experiment. The object of this experiment is to inspect the performance impact caused by thread contention when nothing is done, especially for QoS. First, we divided the benchmarks in CPU 2006 into two groups, and we choose one group as our high priority group, and the other as the lower priority group. Then, for each benchmark in high priority group, just as listed here in x-axis, we first connect its execution time when it runs the low as a base time, and then we connect its execution time again with one of the benchmark in the lower priority group running together. So then the slowdown is computed by dividing the second time to the base time. The data is then indicated in y-axis here. We also has arranged the high priority benchmark, which is more sensitive to resource contention in the left and the next ones in the right. So finally, we have this chart. So we from this chart in the left, which is most sensitive to resource contention, it shows that there are up to 4 times slowdown can happen if, in the worst case, if nothing done, especially for QoS. Okay. So, do we already have some technologies or methods to improve this situation? For example, to guarantee the execution time for the high priority benchmark not easily impacted by the low priority benchmark? The answer is yes. Well, the key point here is that all the impacts or resource contention are originally from some kind of resource share. So if there's no share, then there's no contention and no impact, okay? In a virtualized environment, some typical shared resource for all the VMs run on the same host include physical CPU, memory, I/O devices, and platform shared resources. Well, we already have some kind of ways to control the QoS for some of these shared resources. For example, for CPU, we can assign the isolated CPU for the high priority VM, and we can also assign dedicated memory to the high priority VM. Yeah. And similarly, we can do the same for the I/O devices. And we can just pass through the physical device or the virtual function in SRV keys to the high priority VM. But for the last one, the platform shared resource, such as last level cache, the memory bandwidth, they are all shared by the VMs and the same host. Sorry. Do we have the ways to control them? Unlikely, we don't. Hardware, in the past, hardware just hides all these details in a black box, and the behavior is unpredictable when resource contention happens. So if we can't controlling this shared resource, then it's not possible for us to achieve our QoS goal. Good news is that Intel has realized this problem and had provided several technologies to address them. They are in what called the platform QoS technology, and they can be further divided into 2 types. The first type is resource monitoring, such as the cache aggregates monitoring, memory bandwidth monitoring. The second type is resource controlling, or sometimes we call it resource enforcement, such as cache allocation technology. So with these technologies, or by using one or more of these technologies, now we can not only detect the resource contention, but also we can guide the hardware's behavior to achieve our QoS goal for shared resource, shared platform resource. Well, the vision of the platform QoS is to extend the monitoring and enforcement across the platform. For cache vector, we can say currently we have cache monitoring, cache allocation, and we also have code and data prioritization, which is actually an improvement for cache allocation to provide separated code and data cache enforcement. For memory vector, we currently have memory bandwidth monitoring. This is the roadmap and its enabling status in Zen. Generally speaking, we already have cache monitoring in 4.5 and memory bandwidth monitoring in 4.6. A cache allocation will also be there. In the next release of Zen, there's already code and data prioritization plan, and possibly some future features. Okay, let's see the key concepts behind these technologies. As I have said, there are two types of them: monitoring and allocation. So for each type, hardware provides an interface for software to associate the hardware shared resource to software code. For monitoring, it's ARM ID, resource monitoring ID. For allocation, it's QoS. That's class of service. So both of them are just some two numbers, and they're organized in a new introduced MSR. So each thread, a hardware thread, and the platform has this MSR. But how will the RMID and the QoS be used? This is the flow for monitoring. First, it's software's responsibility to associate the RMID to the software entity. What I talk about is the software entity here could be an application thread, a group of threads, or a vCPU, a CPU for a VM, or what else. Actually, hardware doesn't care for this. It only cares for what RMID is running on current CPU, not CPU. So for each context switch, software needs to tell hardware the next RMID will run. So after software has this information, and after hardware has this information and the software gets running, hardware will do the marketing for resource marketing. And it will mark resource request with that RMID and record the monitoring data in the internal monitoring counter. When software has been run for a while, it then can use the reporting services to query the internal monitoring counter with RMID, and then finally come out the final cache occupiers or memory bandwidth. data. Okay. So there's also a new introduced MSR for this purpose. This is the allocation flow. Similarly, it's software the responsibility to associate the QoS to the software entity. For example, associate QoS to a VM, just like we did in Zen. For each domain, we associate a QoS for it. For cache allocation, we have additional steps to configure how many cache will be used for a QoS. For each QoS, there's a new MSR introduced for this purpose. It represents the cache capacity by using cache bit mask, or sometimes called CBM. Hardware supported the cache allocation technology will first divide all the cache into several equal sub-portions, and each portion has a bit corresponds in the CBM. So a set bit means that the portion of cache can be used by software which are associated with the corresponding QoS, and the clean bit means that portion of cache can be used. So after software configured the CBM for each QoS and associated the QoS for the to the software entity, such as software thread with CPU or what else, in each context switch, then the network will be taken care by hardware. Hardware will enforce the software's entities cache usage according to its QoS and the corresponding cache capacity stated in the CBM. Okay. The thread contention experiment again, but this time with cache allocation applied. Generally speaking, we give more cache to high priority benchmarks and less cache to low priority benchmark. Also note that we give different portions of cache to them, which means the cache portions they will be used are isolated. Just like we did this for physical CPU and memory. So with this configuration applied, the previous contention is reduced substantially. Okay. Well, there's still some remaining contentions here, which is proved to be the impact from the memory bandwidth share in our other experiment. Okay. Well, let's see the implementation in Zen. First, for both monitoring and the cache allocation or resource allocation, the granularity is per VM. That means for each VM, RMID and QoS are associated with it. When any of the vCPU begins to run, the corresponding RMID and QoS is then written to hardware register. Also, we tried to implement the mechanism as minimal as possible in hypervisor, and we left the usage partners as more as possible for user stack. So for in this way, we can reduce the bugs in hypervisor, but it provides the flexible for user stack. For example, we provide a simple API, a simple hypercore for user stack to search the CBM for each VM. But it's up to the user stack or for the user to decide how many cache can be allocated for each VM using the algorithm. That depends on the usage model. Yeah. But if you just want to have a quick try, the XL commands listed here is enough for you, I think. This is a cache monitoring XL example. First step, we need to check if cache monitoring is available. Hardware maybe not support that, and we also have an option in boot line. You need to turn it on manually at this time. If the 70 is supported, then you can attach a target VM to the hypervisor monitor service. After that, hypervisor will work together with hardware to monitor the cache address for that VM. Usually, we will wait for a while so that the data becomes stable. Then we can display the cache address data with the show command here. It will print out the cache address for each socket. As now, now the cache address is just for NAS level cache address. Here is L3. Finally, we can detach it if monitoring to this VM is not needed anymore. This internally will free the ARM ID related to that VM, and then that ARM ID can be used by another VM. This is a cache allocation example. The flow is similar. The only difference is we need to set the CBM for each VM. Well, if you don't set the CBM for a VM, it has the default CBM, which is all ones and which is all ones for all bits. That means it can use all the system cache, just like the machine that doesn't support the CRT. Well, besides the XO demonstration, what else can it do in real usage? Let's see. This is cache monitoring technology used in OpenStack. OpenStack uses cache monitoring technology in two ways. First is for metering. Now cache address can be displayed in the dashboard, which gives people a direct view of the VM workload status. The second usage is what I call lost neighbor detection. So the idea behind this is if the cache used by a VM reaches or even exceeds a threshold value, we are noted for that. Then we can migrate it to somewhere else or some other host, so that the QoS for the VM in the same host will not be impacted. See? So even without cache allocation, cache monitoring alone can be used for improving the QoS somehow. Okay. This is the cache allocation technology being used in FV project optimization. By giving more cache, not level cache, to real-time application and the system core services, we can improve the interrupt latency significantly. Okay. This is an example of combining both cache monitoring and cache allocation to build up an automatic cache adjustment system. In this case, cache monitoring data here is used as the feedback for cache allocation. Then the cache allocation can be fully dynamic or even half dynamic. Yeah. This model can be easily improved by using some of the algorithms or even machine learning technologies. Okay. There are some possible future work. As far as I can see, there are chances for existing feature improvements for both hardware and software, and there are possibilities to introduce the new features and new use models. Yeah, okay. So for one who wants to learn more, there's an additional resource needs. I think you guys can download the slides from the website. Okay, that's all from me. Question?
So you mentioned that you can dynamically change the mask for the CAT. So I'm wondering that when you are changing the mask for process or VM, do you have to flush the cache or just flush the specific partition to write the content back to the memory?
Actually, the cache will not be flushed in the current hardware. Okay. So you will see some. So the actually cache enforcement will be done when the cache flushed later.
Okay, but like if I'm a process running on the cache partition 1 and later you change it to cache partition 2, and maybe I will have the same content at the same address in 2 cache lines if you don't write it back.
Yeah, that is true, but the cache enforcement is just done when the new cache flushed. When new cache eject.
Okay.
Reinforce new entries in the cache.
Yeah.
Okay. Okay.
So if you wind up with a whole lot of cache and you suddenly change your class to a category with less cache available to you, you win for a while.
Okay.
Eventually, you won't.
Okay. Thanks.
There have been in the past a couple of papers regarding monitoring of neighboring VMs for stealing security keys and so on. Do you see how this technology could help there?
Yeah, there are some papers, but now I don't. I think all the materials are from Intel Intel specification and some from websites. Yeah.
This technology is not designed for that.
Sure, I mean, it might not be designed for that, but given that the attack is based on shared last level cache, and this technology might be used to completely separate last level cache usage, that's my thinking.
Already does, so I'm not totally sure. Let's talk afterwards.
Yeah, okay.
Sounds like this is a good long discussion.
Can I extend to that question something like regarding real-time VMs? Is it like giving me more assurances in real-time environments if I have these requirements for guests when I run the real-time version of Zen?
You see the environment we did for that NFV project.
Sorry?
Yeah. Yeah.
Simple answer is yes. We really see this as being a major advantage.
Okay. The other question is, I saw this is, was it introduced by Haswell CPUs?
Yeah.
Yeah, CMT. Yeah. 30 will be in Broadwell.
Is it the whole series, including Atom CPUs and so forth, or is it just Xeon? Okay. Okay. Thank you.
Generally appears to be the server variants that have this stuff in.
Well, but Atom is even different from client variants. That's true.
I'm just asking because of embedded systems or something like that, where you wouldn't put a Xeon on the board.
Yeah, well,
and it might be.
Because of that, probably you can see the same stuff in there, because by the same token, for those kind of embedded systems, they're really trying to keep things cheap for obvious reasons. So I don't know what to say.
Okay. Okay. Thanks.
Any questions? So if no, I think we're done.